So, hello everybody, welcome to my talk. My name is Aniket Kate. I'm an assistant professor here in computer science department, and it is my pleasure to give this talk to you CERIAS members. So the title for this talk is Preventing or Penalizing Equivocation in Decentralized Environments. I'll start this presentation by giving a brief overview of the kind of problems that typically interest me for my research. So most of the things that I do can fall in the category of solving the cryptographic trust problem. What I mean by that is that in many secure systems, we often require an authority who not only protect a secret, but also use that secret when it's required in a particularly predefined manner. So let's say we have this party on there, Alice, and she wants to actually get something signed with an authority, and that's authority has this secret key available. This is our typical public key verification scenario. So what she does is she sends her identity and the public key to this authority. Now this authority just take these two things, verify this ID actually belong to Alice, who authority is talking to, and provide the signature. So here authority is basically supposed to protect the secret SK and use that in a predefined manner. Okay, the question is always how you realize this trusted authority. Okay, there are instances that we always come across where these trusted authorities get abused or does wrong things by mistake or for malicious purposes. And one thing can be you make them accountable, so that if they do something wrong, they will be held accountable. Maybe they have reputation to lose, or maybe they also can have some monetary penalties. Okay. Another thing can be you distribute this authority. Let's say you assume that you pick up different parties who don't collude with each other. For example, like that these three world leaders who we believe will not collude with each other. And we assume that the key is now shared between these guys, so that when you combine all the shares, they get back, they can perform any computation that you want to perform with this secret. The third thing that recently get used is that we can assume some kind of presence of some kind of a trusted hardware, such that this trusted hardware works in a particular manner, protect the secrets, and use that only in a particular fashion. In the talk today, we are indeed going to see the combination of these techniques in an interesting problem. And the problem that we are going to discuss today is equivocation in distributed systems. So what is equivocation? We say that a party equivocates if it sends conflicting messages to different parties when it is supposed to send the same message or the related messages. Okay, let's say you want to send party value A and other party value A, or maybe some relation, some related value like A plus 1, and the value is not sent. That's when we call the equivocation has happened. And this is maybe we can say a general definition for several things that we see in the various distributed computing scenario. For example, if you take the electronic cash, then double spending of the cash, because it's just a digital money and you can copy that, then double spending in electronic cash is example of that. Or maybe when somebody signs multiple public keys for the same identity, that can be also an example for the same thing. Or let's say somebody provides you a stale entry of your BGP or DNS record, that's also a form of equivocation only. Or maybe even the other example can be inconsistent software updates. So these are just few examples, and we see that in most of the distributed systems, or in general most of the centralized systems that we come across. The traditional ways to solve these problems follow in three categories. The first is that you distribute the parties and you allow to have higher replication factor. For example, if you take standard distributed computing protocols, in that case, if you do not have equivocation, that means your adversary can only at best crash. And in that scenario, you only require honest majority. So what I mean by honest majority is that if you have n parties, you can allow at most half of them to be malicious, or half of them to be adversarial. However, instead, if we go for the equivocation, and if we allow some active attacks, in that scenario, indeed this honest majority has to increase to the 2/3 majority, and that's why we get this bound of n greater than 3t plus 1. Okay, so by having a higher replication factor or row resilience, you can achieve the protection against the equivocation. Another thing is we assume synchrony and digital signature. We say that every message that I get, I'm going to send to all other guys, and this message is signed by the sender, so that if sender is doing something wrong, we all will collaborate and find it out. Okay, and that's also another thing that is typically used to avoid the equivocation. Or more recently, people say that why can't we use trusted hardware? Now this hardware ensures that every message that goes out is sent in a particular manner, so that you just can't create two messages for the same index, same context there where you want to send the message. Okay, and our focus indeed will be on the third aspect much more in this talk, especially the first part of the talk. So this talk is indeed talks about how considers the problem of equivocation and how we solve it. And the first aspect will be considering how we prevent the equivocation using trusted hardware, where in particular we are going to look at the concept of transferable non-equivocation and how to use this transferable non-equivocation to the problem of general multi-party computation. While in the second half we see that there are situations where we just cannot prevent equivocation, but maybe it's possible to somehow penalize every equivocation instance. And in their second half, we are going to see how to penalize that with cryptocurrencies such as Bitcoin, and where we are going to see very interesting aspects regarding that. And in particular, we are going to look at some smart contracts based on Bitcoin. And a particular example that we are going to see is asynchronous payment channels. So the first aspect is preventing equivocation using trusted hardware. So this is based on two of my recent publications from Principle of Distributed Computing 2012 and 14. And basically what we are saying here is that we just prevent equivocation by making it not possible. Okay, so before we do that, this work is relying on asynchronous communication setting. So maybe some of you have already taken distributed systems here. But if not, there is a difference between synchronous and asynchronous communication scenario that we typically employ in all these settings. Okay, so the synchronous, or more specifically bounded synchronous scenario, says that our communication among all different participants is always bounded in terms of rounds. So there are all the communication happens in terms of rounds, which are predefined, fixed in terms of time. And you expect that whenever any party send message to any other party, they reach the recipient in this time bound. Okay, if you are expected to hear some message from some party in a particular time period, and if you do not hear that message, then you also know that this party is crashed. As for example here, the example that I'm showing, Alice knows that the message that Charles has crashed. Okay. While in other more generic scenario, which is called asynchronous communication, you just can't have such bounds on time. So instead, in those scenarios, you rely on that. You depend upon how that when you are supposed to get a message, you know that the message, if it is sent by an honest party, it will never get lost. But you may have to wait for any amount of time. So that's a asynchronous communication scenario is a generalization which is provided as a help towards really replicating as the worst case scenarios for the internet. And there the key challenge is always, because there are no predefined round, it's very difficult for you to differentiate between whether the sender who is supposed to send you a message is crashed or is just slow. And that makes the designing protocols in this asynchronous scenario slightly more difficult. Okay, so we are going to assume the asynchronous communication scenario here. In particular, we assume that there are different distributors, there are different parties or processes which are distributed. They all have channels with each other. Okay, but these channels are asynchronous, such that the messages, when they are sent, they can be arbitrarily delayed or reordered. Okay, but what the model assumes that all the messages are eventually reached to their destinations if the sender is honest or correct process. Okay, and in that case, we typically consider our typical two adversaries: an active adversary who can try to do all sort of malicious attacks, and a crash adversary who may only crash, who will not send incorrect message, who will not do equivocation. Okay, and we consider these two adversary scenarios to show the differentiation between what are the effects that we have because of the equivocation. By the way, if you have a question, please stop me at any point of time. Okay, we don't need to wait until the end. So as we have already seen, the equivocation indeed has issues in terms of in the asynchronous setting, asynchronous communication setting. So we saw this difference that if we are in this crash, if our adversary can only crash, then an honest majority, which is n greater than 2t plus 1, where n is the number of processes and t is the faulty processes, so we only require honest majority. But when we have active adversary or Byzantine fault, then this increases to 2/3 majority. And as we mentioned, using trusted hardware, we can actually reduce this bound required to just 2/3 to just honest majority. And this has been studies already in the literature in the form of two main works. One is called attested append-only memory, where they assume that every process has access to a memory where you can only attest to that memory. So you have a log and you can only add to that log. You cannot remove things from that log. And using that assumption, they are on every process, they are able to reduce this bound required from 3t plus 1 to 2t plus 1. Okay? The more simplification came a couple of years later when they showed that just using a simple trusted counter, so only thing that you have in the trusted hardware is a counter. So your message is that any message that get out of your system, a new counter value get added to that message and the counter get incremented. Using such increment-only counter, it is sufficient to actually avoid all sort of equivocation and get the lower bounds. Okay. Saying this, what's happening this a bit more formally is that let's look at this this particular sentence. So we say that we define a context when we want to send a message. Okay, that context can be you're spending some money or you're supposed to sign a public key. This defines a context. Okay, and it can be any string, and then in any given context you are supposed to make a statement. Okay. Now what non-equivocation says is that with non-equivocation, it allows validation of a pair, which is a k comma message, where k is the context and m message is the statement that we make, from any party, such that all other participants who are particularly interested there cannot make another message, which is MSG prime here, and make that associated with the same context. Okay, so once I fix my value of k and I assign one message, that message can be malicious, I don't care, but I assign some fixed message or some fixed statement to that context, then I cannot change the statement for the same context. Okay, and if you look at, if you want to just get the relationship with a trusted counter, in the counter the value of the counter will be my context, and I can assign any message that I want to assign to that. But once I assign a particular statement to that particular counter, then counter is going to increment, and I cannot assign some other statement to the same counter. Okay, so that's the concept of non-equivocation. And interesting thing to see here is that this only assigns the statement, and from more distributed systems point of view, it's a safety or integrity guarantee and not a liveness guarantee. What I mean by that is that when two participants, in our case let's say Alice and Bob, they receive two messages for a given context k, then they are going to get the same message, so that my message and the red message and the blue message, they are just the same. They have to be same in the non-equivocation scenario. However, it's very easily possible for adversary to just not the send message. Okay, it does not stop. I mean, it can just say behave as if it is crashed or just slow, and not send the message. So in this example on the right hand side, as you can see that the message is sent to Bob but not to Alice. Okay, so that's why the liveness cannot be ensured in such a scenario. Now what we observe that because of these particular things, what was assumed in the literature that using non-equivocation we can get the replication factor down is actually wrong. What we observed, or rather what we are able to prove, that in the asynchronous setting, tolerating active faults, non-equivocation alone does not allow reducing the number of replicas or number of processes that are required. We already know similar thing for the signatures. Okay, that in signature scenario, only signature by themselves in the asynchronous case are not sufficient. Instead, all these previous works, they use the they use the signature inherently along with their non-equivocation. So, and this can relate to a concept of transferable non-equivocation, that is non-equivocation plus digital signature. And what we observe that when we make this combination, this is useful to actually do much better things and reduce the replication factor required. So just to give you example why this makes sense is that we already saw that the liveness is the issue. That it's not always the case that adversary can just stop sending some messages. Okay, and that's one of the reasons that we got the above results. However, when we also provide the digital signature, they have an interesting characteristics that here, let's say our Bob participant, he got the message K and message prime. Because of the digital signature characteristics, he can not only sure that he can get this message and be sure that he got it, but he can forward this message to Alice and knows that if the message, when the message from Bob to Bob reaches Alice, even she will be able to make sure that this is the correct message. Okay, so that's how, because of the digital signature, you get this transferability of equivocation tags, which allows you to overcome the barrier of n greater than 3t plus 1. Going forward, what we are able to show that it's very generic result in the sense that we can take any crash fault tolerant protocol in the distributed computing scenario, and we can attach to that transferable non-equivocation, and then we can achieve a Byzantine fault tolerant protocol. Okay. And the key advantage here is that now using this trusted hardware, we are achieving Byzantine fault tolerant protocol. In most normal scenarios, this involves typically not only addition and replication factor, but also it also adds the number of communication steps that you need to perform. But using the transformation that we provide, we can not only deal with the replication factor for the crash setting, which was honest majority as we already saw, but the communication steps that required are also reduced to the step of crash failures. Okay. Going forward, we however observe that this transformation that we come up actually does not cover the privacy or the secrecy property that we required in the cryptographic systems or protocols such as multiparty computation. So distributed computing protocols are like reliable broadcast or consensus agreement, these kind of protocols. So where there our generic transformation help, but not immediately into the cryptographic system. Yes?
Just a quick question. It's not immediately clear. Maybe give an example.
Use your mic, please.
Could you maybe give an example of, do I understand that this non-equivocation adversary is strictly weaker than the Byzantine adversary?
No, this adversary is as strong as just we put a restriction in terms of the non-equivocation, that you assume it's a Byzantine adversary, but it just cannot send the message because in the protocol level.
But he can send incorrect messages, which the domain
then
of this
they
is
will be
unbounded.
dropped out, because every message has to associate it with some kind of a tag or some information saying that a tag which is coming from the hardware. And if that message that you send and the tag, they do not match with each other, then you are going to throw that message. That's the power that the recipients have.
So it's strictly weaker than the Byzantine adversary.
Okay, go ahead.
No, I guess my question is
no, it's a different. I mean, your adversary is strong. Your setting, your communication or system setting has other provisions to take care of that. That's the way to look at. But maybe we can also look at that using strictly weaker.
Yeah.
Okay. All right. So we saw that examples where indeed we get general transformation, but this does not work for the cryptographic protocol that we may interest. And in the next work, where indeed we try to develop a system that when we also want the privacy properties or secrecy properties along with the standard safety and liveness property from the distributed computing protocols, what we need to perform. Okay. So in general, we the concept that we develop is called transferable non-equivocation for asynchronous multiparty computation. Yes.
Sorry. Just a quick question. The previous result applies to what liveness property?
So whatever is possible with the standard crash protocol will now go to the. So it does not introduce. Yeah, that's a good point. It does not introduce a new liveness property. It just actually whatever liveness property is possible for crash protocol now will go to the Byzantine fault tolerant protocol. Yes. So for those of you who do not know the problem of multi-party computation, it's a generalization of problem that we solve in cryptography. So we assume that there are n parties and each party has a private input. And in multi-party computation protocol, they want to compute some particular function on their input. All right, so let's take an example on our right hand side. There we see that, let's say there are four different participants, Alice, Bob, Charles, and Donald, and they want to work a particular function f, let's say a parity function on their inputs. Okay, so what properties that we want from the MPC is that the first thing is correctness. That means in the end, when the output comes and whoever that output is available to, they get the correct output. Okay. The second thing that you want, privacy, which is a critical property here, that it should not be possible for our adversary to know anything more than what they can find out from the output for the input that is provided by all the participants. Okay. And the third thing that we want is termination, where we want to indeed finish this protocol. If the protocol does not finish, it is of no any use. Okay. So these are our goals, and the typical assumption that we work on here is that indeed we assume that parties are connected by pairwise authenticated channels, so that they can know whom they are talking to, and we are working in the asynchronous communication setting, and our adversary is also computationally bounded. Okay. In this setting, it is known that we will call this protocol as asynchronous MPC or AMPC, because it's a protocol in asynchronous communication setting, and we required again 2/3 majority, or rather n greater than 3t plus 1 also in this setting. And the question that we want to study is that what can transferable non-equivocation can do for us in this particular setting. And one way is that indeed we can go to the synchronous setting and solve this problem, but that we want to avoid. So what we are able to achieve that with certain special requirement which are specific for the MPC, we are able to use the transferable non-equivocation and obtain the result where the multi-party computation in a generic manner is possible for honest majority. Okay, the protocol that we developed required actually a cubic communication in terms of the number of users, and where the kappa here is just a security parameter. And it required the threshold encryption and homomorphic encryption, but not threshold homomorphic encryption setup as with the previous work. And the key component that we developed here was a asynchronous verifiable computation protocol, which is the key component that we use here, and that's also something which was not previously available in the literature. So just very small 101 on asynchronous multi-party computation. Here typically your protocol, the computation that we want to perform, I'm showing on the right hand side, and there you can see that there is the typical first phase there is the input phase, where what we do is that we take the input from different participants and secret share them, so that now they are available in a shared manner to all the participants, such that nobody knows a particular any of the secret, but they have some share of it which they can play or do any computation afterwards. The next thing is the computation phase, where basically you take your computation that you want to perform and you represent that as an arithmetic circuit and perform all the operations of there, especially additions and multiplication on this arithmetic circuit to obtain your output. Okay, and additions are local, while multiplication requires some special technique that we are going to see. And finally, once everything is ready, you take all these inputs and combine them together to get the output. Okay, so these are the three steps that we generally look at most of the multi-party computation protocols. And as you can see there, the additions are local and immediate. The key task is always the multiplication. So multiplication means that I have provided, let's say, input from two participants, x from some participants and y from some other participant, and we want to multiply this input. Okay, so that finally we get the multiplication of those two input in a shared form. That's the goal. And as it turns out, this is a critical task, and the most standard technique to do that is concept of a beware circuit randomization, where they use a particular mathematical identity, which given another random pair of u, v, and multiplied and a sharing of some value u, some value v, and product of them, that is u, v, you are able to use one pair to compute the other pair which is of your interest. And then idea is to generate all these required u, v, and u comma v and comma u multiplied with v pairs, several of them in the pre-processing phase, and do the multiplication based on that. So for all those of you who want to see, when you want to solve multi-party computation, we always want to just generate such triplet, and once you got this triplet, the task afterwards is very easy. So this triplet is typically known as supervised triple generations, and that's where the major task in the multi-party computation has to perform. In our case, this typically just shows the steps that we follow in our generation. We don't have to worry about that too much here. The key thing will be we are just going to pick the basic building block that is required in this setting and just try to see what is this building block and how we actually develop this building block using non-equivocation. And that building block is supervised sharing. As it turns out, this supervised sharing is almost equivalent to a generic concept or well-known concept of verifiable secret sharing. So verifiable secret sharing is a extension of standard secret sharing, which some of you might already be knowing. But the idea here is that you have a dealer. That dealer has a secret, and that dealer wants to distribute the secret among several parties, such that some of them, a predefined subsets of them, can come together with their shares and reconstruct the value as and when it's required. Okay, you have guarantees such that it's indeed when those shares come together and they are reconstructed, you get the secret that is provided by the dealer, even when the dealer is malicious. And his whole issue is to just provide some randomness and create a chaos among those participants. So in the example, I'm showing 4 participants there, which are getting their share 1, share 2, share 3, share 4. And the key property that we required is that if we take, let's say, any 2 of these shares, as I'm showing there, and you use a well-defined algorithm, you always get the same secret. Okay. However, the privacy property here is that when you just take one of these participant and their share, let's say share 1, that is not sufficient to actually know anything about the secret S that dealer has distributed. Okay. Now the question is how you actually compute this verifiable secret sharing in a synchronous manner. So it is a well-known result that for this particular verifiable secret sharing itself, you required a 2/3 majority. Okay, and you required private channels and cryptographic commitments to achieve this this computation. If you want to really want the properties of such as termination, then you required n to be greater than 3t plus 1. Okay. I'm not going to go into the detail of that protocol. Its protocol is interesting but complex at the same time. But I'm just going to give why we require these 3t plus 1 parties. Okay. So the general idea that is here is that in asynchronous scenario, we can never be sure if somebody is slow or crashed. So we cannot always wait to hear from all the participants for their information if they are supposed to send you something. So instead, the idea is always you give away t of them. So once you got n minus t messages, you say, I'm going to just stop here and continue working on your protocol, because others maybe just crash and never come back to you. Okay, so that's why we cannot wait for the last t parties, and that's why we get this bound that n has to be greater than, or the bound should, the number of answers that you hear has to be greater than n minus t. Next, and this is called consistent sharing. Next, it may be that the adversary already know what you're doing, and he's going to already push his messages to you, which are wrong. Okay, and for that case, the messages that you receive can be wrong, and that's why the amount of number of messages that you receive, out of that also you should have a levy that you give away any T of those messages. And that's the reason that we further has to remove another T participant for there, and which allows you to then go for n minus 2T. Now to do any reconstruction in a meaningful manner in the standard secret sharing, you have to get at least the shares from the T plus 1 participant, because T is the participant that you have the security against or the privacy against. So that's why in this such a particular setting, we have the requirement that n minus 2T, the requirement that I'm showing in the last box, is that this n minus 2T has to be greater than T plus 1. And once you substitute, make this equation right, we get that we indeed required 2/3 majority or n greater than 3T plus 1 to run the verifiable secret sharing protocol. Okay, and let's say we just introduce non-equivocation. This immediately does not work over there, because let's see if we introduce the non-equivocation there and we reduce the number of parties to 2T plus 1. In the final box, we can only have one participant on the right hand side of the equation. Okay, so we are in secret sharing scenario, and we have this one participant, and somehow he is providing all the necessary information to everybody else, all the other honest parties. But that's not the way to go, because then how we achieve the confidentiality, because then he knows all the information that has to be known. So what we observe here is that along with non-equivocation, we also need encryption. So that the idea will be now, rather than doing just giving the shares, I'm going to encrypt all of my shares for their respective recipients and then push that to all the participants. Now in this case, even when one participant got all the encrypted shares, the only thing, he doesn't know what's written there inside, and he is only going to forward them to the respective receivers to eventually receive the values that they want to receive. Okay, and that's basically the idea here. That we observe that synchronous verifiable secret sharing is possible for honest majority, and this we also observe in the crash failure model. And basically then we require encryption there, and then use encryption and the non-equivocation aspect to really get the idea through for the malicious setting. So the very simple protocol here can just look as simple as what I'm showing here. Let's say we assume that a dealer who generate all the shares, he encrypts each individual share for their respective recipient, and he just flush that or send that to everybody, just flood the network. Everybody just gets their value, get their shares, okay, and then send all the other shares to the rest of the network. Now in such a scenario, as long as and then it commits that, oh, it got the sharing, because as long as you have some honest parties, they will eventually send the message to all other honest parties, and they will get their shares eventually. Okay, so that's how the whole protocol works. However, this protocol has communication complexity of n cube, because every party is sending n messages to all other parties. So that's why it's n square, and that means in total, if you add this up, this will just become n cube protocol. Okay. However, it's possible to use digital signatures again along with this to actually reduce this communication to only O of n square. I'm not going to show that protocol, but it's certainly possible. Now our idea will be, we take this protocol, which is only crash fault tolerant, and make it tolerate now also the Byzantine fault using transferable non-equivocation. Okay, and the transferable non-equivocation, basically what we achieve is that in our scenario, transferable non-equivocation is going to ensure that the adversary do not send two different sharings when it is supposed to send the same sharing. Then we are going to use zero knowledge proof to ensure that the encryption that we got are for a correct secret sharing, because he may just otherwise send some garbage out to all other participants. And finally, we are going to also use signature to ensure reduce the communication complexity. And with that, the idea is to then develop the whole protocol and build the whole multi-party computation structure on top of that. So in general, what we saw here, that non-equivocation on its own does not allow reducing the number of processes, and we require transferability. But instead, if we have a small trusted hardware assumption in the form of transferable non-equivocation, that can be useful for in the asynchronous setting for multi-party computation, and for that matter all distributed computing protocols. And the encryption of the requirement of encryption and zero knowledge proof was certainly a bit came to surprise to us as well. Now moving on, we are going to look at slightly different scenario, which is that penalizing equivocation. So many times the prevention of equivocation may not be just possible. So if you look at the standard scenario of using synchrony and digital signature, I got two different messages signed from the same participant. I know that he is wrong, and I can maybe remove them from the system. But in many distributed systems, such as social network or whatever, we always have weak identities, or we always have identities which have privacy requirement. So although when somebody does something wrong, we may not be able to determine who is the real person behind that. We may bar their currently used identity, but they can just go ahead and pick some other identity. Okay, so as I'm showing in that figure there, basically adversary can just create any number of civil IDs and keep on employing a new ID every time it does something wrong. Okay, and it's a problem. And then the question in this scenario is that how can we actually stop adversary from launching such civil attacks, or such attacks where he just keep on shifting identities. Okay. The first thing to see is that how we solve this problem in real life. So real life, what we solve this problem is that anything we make contracts between two participants, and the idea is that they both are supposed to follow this contract. If they break the contract, the idea is that they have to lose some money. Okay, and there will be an arbiter who will just look at what things has gone wrong, and basically then punish the participant in terms of some monetary compensation, or maybe can be legal proceeding. Okay, the issue with such a system is that we have single point of failure in terms of this arbiter, because you have to protect its security and availability, you have to protect the privacy, that it does not leak some information such as your identifiers, and it may become unfair in some scenarios. And the question that we ask is that can we use decentralized currencies because there is no central party such as Bitcoin, and create this contract based on Bitcoin? We are going to call this contract a non-equivocation contract. So the idea will be you associate the contract that two participants are making and map that contract to Bitcoins. Okay. Let's take a very simple example to understand what's happening. So let's say there is a party who is on left hand side, and this particular server is supposed to send two messages to two participants, let's say Alice and Bob again. And what he says that unless I follow this some requirement, I'm setting this money, which I'm showing there is in Bitcoin, aside, and if I do something wrong, the money just goes to the participants. So let's say adversary become malicious, and then it does something wrong in this particular contract. Because these contracts are made, the money will just basically get transferred to the Alice and Bob, or for that matter some other participant. Okay, so that's the idea of penalizing equivocation using Bitcoin smart contracts. Okay, just to make it clear, let's look at an example very quickly. Let's say we have a small data structure where there is a server, and the server is supposed to maintain a state level data structure, let's say state A, state B, and state C. And the equivocation will happen then when it actually it does not follow this chain and basically divert at some point, such that one participant sees state D while the other participant sees state E. Okay, and what we want here is that this can be looked at as an integrity of some cloud storage or many other things. Okay, and in this scenario, what we want to ensure that that when such thing happen where our Bob sees state D and Alice sees state E, then because in standard scenario what can happen is that they can actually talk to each other and see that, hey, something has gone wrong, and basically then blame the server for the wrongdoing, and probably just get some law and authority or some trusted third party involved in this process, and convey them that something wrong is happening in this scenario. Okay, but that is only possible when this reputation is the key factor for the service provider. If on top of that let's say they don't worry too much about the reputation, in that case it might be interesting to actually penalize them in some monetary manner. So what we'll be doing here is that, let's say that this central service has kept some money aside as maybe self-blackmail, we can call that. If I do something wrong, this money goes to you guys, or maybe something wrong happens to that money. And let's say it sends to such equivocating statements, and then these two guys talk to each other, and now this money can vanish from there. So the money can just disappear, or maybe it now is available for Alice or Bob, or some other combinations can be possible. Okay, so such a contract, when we look from the Bitcoin point of view, the way it will look like is like that. So we assume that both the contractees, which I'm showing at the two extreme ends of my slide, they are generating a public and private key pair, okay, such that they know each other's public key pair. And what they're going to do is basically create a contract which can be open only when both of them sign that particular contract. Okay, and typically in such scenario, it's also possible to add a time limit, so that because the server on the left hand side do not want to just keep money always hanging for the rest of its life. So you can put a date there as if that this contract expires on this particular date. But to spend money before that, both of them have to sign this, okay? Or after that time period, now the signature from the left-hand side server, the contract initiating server, is sufficient to spend this money for any other purpose, okay? But with one caveat, that let's say when server equivocate in a particular manner, then it's possible to take these two equivocating statements, do some computation such that the private key that is used by the server pops out, and now you have both the keys available to you, which you can use to break the money and take this money to the recipient on the right hand side. Okay, so that's the way to look at this contract. And the question is again, who is this party on the right hand side? And there are different versions that we observe are possible. A is that you can pick a particular participant or particular player, and that player is supposed to get this money. It's also possible that there is a concept of miner in Bitcoin. These are the guys who generate the currency, and it is possible to make them also receive this currency. And it may be just very well possible that the money get burned, that nobody can use it. Okay, so all these different things are possible, and in all these scenario, we use a particular feature in Bitcoin which comes under an opcode called check lock time verify, and once that is available, all the options are available, will be possible. As of today, the first and the third options are immediately possible. The second option is not yet possible, but maybe in a month or two, even the second option will become possible. Okay. However, it looks magic, right? You are providing two signatures, and all of a sudden, you get if two signatures on the same context, you get the private key out. It looks magic, because how come since when the signature started to give away the private key? And that's why we have to introduce a new cryptographic primitive here, which we call as accountable assertions, which basically allows you to make assertions or make statements which you can be held accountable for. Okay, so the general idea is very simple. We make assertions, or the statement that we saw here, and similar to our equivocation concept, we have context and we have statement. Okay, and then idea is that basically it should not be possible for you to make two different statements for any given context. Okay, if you do that, then you have something to lose, and in this case it will be a private key for your Bitcoin account. Such a primitive can very easily be seen as a statement where you have a assert command which is available to this the server, who can who can use some secret key, a context and a statement for all different kind, and send those statements to the recipients. And recipients can verify, given a public key, that this context and this statement indeed makes sense for the information that I know the adversary knows. However, with another caveat, that let's say it makes the two conflicting statements. So you can see on the slide that I'm keeping the context same, but I'm changing the statement. And in that case, the private key pops out. Okay, So that's the property that we want. At the same time, then it should not be possible for an adversarial user to just ask for two different statements for the same context, and then now use that to get the private key and then break the whole system. So conceptually, we also want the secrecy for the server, that his secret key is not leaked in any other scenario. And without going into the detail, we are able to achieve that with the known cryptographic techniques. In particular, we were able to use the Merkle tree chameleon hash functions, and and the combination of that, and associate that with the elliptic curve that are used on Bitcoin to get our construction. What we achieve using that is basically, once we use the key pair that is used in these accountable assertions to be same as the key pair that I use in Bitcoin, then it's possible to actually create the contracts where any equivocation will lead to loss of Bitcoin. Okay, so that was the overall high-level idea, and that we are able to use in various different application scenario. The most prominent one is a synchronous payment channel, where the idea is we have a concept of payment channel on Bitcoin, which allows the adversary to make a channel so that they already say that I'm going to spend with this bus company, let's say $10 over the period of 1 month or something like that. And whenever I make such payments, eventually I spend little bit of that. So it's similar to our gift cards. Okay, the advantage of such payments is that it allows you to do transaction very fast, and it's also very scalable for the system. So the example for this can be, let's say Bob here is going to spend $5 over the time period with this particular authority. So it can just basically keep spending one at a time, and slowly these channels get filled. All right. And the equivocation in this scenario can happen when, let's say we have Bob who actually tries to spend the same thing with two different applications. And this can happen when these two applications use the same payment channel, but they are not synchronized with each other. And that's why we have the name asynchronous channel. And in this case, then the question is that how we take care of that. Finally, when these two buses, they reach their destination, they'll see that, hey, somebody double spent with us. But as in typical Bitcoin scenario, we do not know the identity of the user. We cannot ban anybody immediately. And that's an interesting problem. What we observe that we can use our payment channel along with our accountable assertions, leading to non-equivocation contract, and solve this problem. In principle, the idea will be, if such a non-equivocation happen, I will lose all the money that is available on the payment channel. So I do one wrong payment, and I lose the rest of the money on my payment channel. Okay, so there are other applications that we work out, and I'll be more than happy to talk about them later. But here I'll just end with this particular example that I gave, and provide a summarization here that not always it's possible to prevent the equivocation. There are scenarios where instead we will have to penalize the equivocation, maybe through monetary or maybe through loss of some information. And what we saw here example, which is where we penalize people based on the Bitcoin contracts, in the sense that when they make some conflicting statements to each other, then it's possible for those recipients of the statements to come together and make this adversary or this server who made conflicting statement lose their money. So with that, I'm finishing my presentation, and thanks a lot for listening to me. Questions? All right, then I guess we are anyhow running out of time. So thanks a lot.